you are in second year only, so you will face lot of problems unless you actually develop a habit of attending classes. This must be understood by your fellow students. Okay. All right. Can you see the screen? Is it visible?
Yes, sir.
Okay. So I was discussing the graph theory. Okay, graph theory, basic cut set, then basic loop, and incidence matrix. These are the three matrices we have discussed, and also we have shown how these three matrices may be useful in actually writing different network equation, network laws, and also in expressing some quantities of the network in terms of some other quantities. So these things already we have seen. Now let us see how these matrices may be utilized to develop network equations. Okay, full network equations where there will be different type of sources, there will be impedances, and then how these networks may be, these graphs may be useful. Okay. So C transpose Bt we have seen. That means what we have seen? C matrix we have seen. C IE equal to 0. It is representing Kirchhoff's current law. C is the Kirchhoff incidence matrix. That means basic Kirchhoff to element incidence matrix. Then also we have seen C transpose Bt that will represent Be element voltage. That also was seen. Then already we have shown that B times V equal to 0, it is the Kirchhoff's voltage law. Then B transpose I loop, this is equal to IE, element current. B transpose loop current equal to element current vector. That is also discussed. Then A times IE equal to 0 is the Kirchhoff's current law. IE representing the current, element currents of the system graph, and then A transpose Vn equal to Ve. Vn is the node voltage vector. A transpose Vn represents the element voltage. These are the things we have discussed in the last class. Now today, let us now go for a generalized representation of a branch. Why this is necessary? Because you see that we have considered different matrices. Now sources are also to be included. Voltage source, current source, all these things. So let us see how we can actually introduce a network element such that we can consider both voltage source as well as current source. What is the basic difference between voltage and current sources? In a voltage source, we see that there is a generated voltage with series impedance. In the current source, there is generated current in parallel with the impedance. So this is the representation. Okay. Now, therefore, so that we can actually include all type of sources and all types of elements, let us assume that these will represent the general branch of a network. Okay. This is a generalized branch of a network where we have the impedance in series with the impedance. There is a voltage source, and across this combination there is a current source. Current source is given to be ISK, source current of branch K. That's why ISK. Voltage source is VSK. Voltage source at branch K. This is branch K, say. Current flowing through this branch is say IK. Okay, and let us assume that ZKK, this is the self-impedance of this branch. This self-impedance is ZKK. That means this is the impedance. So self-impedance we actually say when we also discuss the mutual impedances. So we shall be introducing mutual impedance later on. That's why kth branch impedance, let us denote this by ZKK. So these are the elements. Okay. Since this is the current flowing through the element, to kth element, so the impedance of the element IK is the current. So here, this is the direction of the current source coming out from this terminal, entering here. So this is the total branch, okay, kth branch between the two nodes. So if current IK flows here, so IK flows and comes here, and if ISK goes out here, so here the current entering into the node will be IK minus ISK. Current is IK minus ISK. Similarly, here current is IK minus ISK because IK minus ISK plus ISK becomes IK. So outside this current source, current is IK minus ISK. So this is the current of this element. That means IE, element current. For kth element, current is IK minus ISK. Okay. So this is representing the generalized branch. That means why it is generalized branch? Because this particular branch can represent any type of network element. How? Let us consider that we want to show that this can represent the branch impedance only, not any voltage source, not any current source. In this case, what we have to do? We have to put VSK equal to 0. Also, we have to put ISK equal to 0. So by making VSK equal to 0 and ISK equal to 0, you can say that the network branch will represent simply an impedance of value ZKK. Okay. Similarly, let us assume that this branch should represent a voltage source with series impedance. Then what to do? Make ISK equal to 0. That will represent the branch as a voltage source with series impedance. If you want to represent this branch as a current source, then make a VSK equal to 0. So in that case, that will be a current, there will be a current source. In parallel, there will be an impedance like this. So this particular representation of the branch can represent voltage source with series impedance, can represent current source with parallel impedance. Also, it can represent a simple resistance or simple impedance ZK. So this you can say this branch can represent any type of network branch. That's why this is the generalized branch representation. Okay. Now you see that here, what is the element current? If this is a generalized branch representation, what will be the representation in the graph? It will be simply a line to represent the this element. There will simply a line between the two nodes. A simple line will represent the source and all these things. Okay. What is the current in the element? It is IK minus ISK because this is the kth element. What is the voltage across the element? It is Vk minus Vsk. What is Vk? Vk is the drop in the branch impedance. That means Ik into Zkk is Vk. Vk is the voltage drop in the branch impedance. It is Zkk into Ik, and this is the source voltage Vsk. Okay, so here obviously current flows from a higher potential to a lower potential. That means this potential is higher with respect to this terminal. So what is the voltage here? It is Vk minus Vsk. For Vk, this is the higher potential and this is the lower potential, and for Vsk, this is higher potential, this is lower potential. So if we consider the voltage along this direction, it's the direction for the rise in voltage, then it is Vk minus Vsk. Okay, so Vk minus Vsk is the voltage across the branch. Current through the branch impedance is Ik. Source current is Isk. Voltage source voltage is Vsk. Self impedance of the branch is Zkk. Okay. So now you see that this particular arrangement, this particular representation can represent anything in the network branch. A voltage source with series impedance, a current source with parallel impedance, and simply an impedance also may be represented. All right. Is it clear to you? Everybody, is it clear? So this will be the representation in the graph. In the network graph, this will be the representation. Ik minus Isk being the current entering into the node, that means this is the element current. Vk minus Vsk being the voltage across the node. All right. Is it clear? Now considering that this therefore represents the generalized network branch, this notation we shall be utilizing to develop network equations. How? Now you consider, see that previously what we have written for writing the KCL, what we have written, A times IE equal to 0. A element current vector equal to 0. So here in our case, what is IE? Element current is basically each current will be represented in this way. It will be the current through the branch minus the source current. Okay, is the element current. It is I1 minus IS1, I2 minus IS2, I3 minus IS3. If 1, 2, 3, these are the element number, and IS representing the source, current source. So we can say that A times IB minus IS, this is equal to 0. This is the Kirchhoff's current law. Also using A matrix, we have derived the expression for, or derived the relation between the element voltage and the node voltages. It was A transpose V node equal to VE. This was done in our previous class. We have seen that A transpose V node Vn equal to VE. Now V will be equal to how much? It will be VB minus VS. Okay, what is VB? VB means vector of node element voltage drop. Vector of element voltage drop means in this particular case it will be Z1 into I1, sorry, Z11 into I1, Z22 into I2, like that. Okay, Z being the branch impedance. Z being the branch impedance, current through this branch multiplied by branch impedance is the voltage drop. So that is represented by VB. Vector of that voltage drop is VB. And what is VS? VS is the source voltage vector. This is the source voltage at node at element. Okay. So for all the elements, there will be similar voltages. Okay.
Sir,
All
sir,
voltages
VB tag repeat
equal
করবেন
to- Huh? Follow?
VB tag
VB. VB is the voltage drop across the branch impedance. What is the branch impedance? In this case,
Sir,
uh,
sir,
voltage drop is
sir,
voltage drop is ZKK into IK. Okay, ZKK into IK means for element 1 it will be Z11 into I1. For element 2 Z22 into I2. Element 3 Z33 into I3. When all you actually consider all these elements together, then that vector will represent the element voltage drop vector, okay, or branch voltage drop vector. So VB, that is written by, represented by VB, okay, and IS representing the source current vector. What is the source current at through element 1? At element 1, what is the source current at element 2? What is the source current at element 3? Of these things, all these are represented in IS. So we can say that this equation, say A times IE means A times IB minus IS equal to 0. IB means I1, I2, I3. That means through the branch impedance, what are the currents? That is represented as a vector. What are the source voltages? That is represented as the vector. Source currents represented as vector. So AIB minus IS equal to 0 means basically AIE equal to 0. Kirchhoff's current. And A times Vn equal to Vb minus Vs. Okay. A times Vn equal to Vb minus Vs. Node voltage, and what is Vb? Vb is the voltage drop in the branch impedance. That is branch impedance multiplied by current flowing through the branch impedance. Z11 I1, Z22 I2, Z33 I3. Assuming there is no mutual coupling. If there is a mutual coupling, then it will be modified. How it will be modified? We shall discuss. Okay. And Vs is the source voltage vector. What is the source voltage at branch 1, branch 2, branch 3, branch 4, like that. Okay. All these sources taken together constitute the Vs vector. Okay. Similarly, by using B matrix, we had written an expression B times V equal to 0. If we modify that using this generalized branch representation, that will be B times VB minus Vs equal to 0, because element voltage is element voltage at element K or at branch K, it is Vk minus Vsk. So V1 minus Vs1, V2 minus Vs2, like that. that may be represented as this is VB, okay, and this is VS. So B times VB minus VS equal to 0. Similarly, we have written B transpose I loop equal to element current IE. So what is the element current in our case? Now element current becomes, it has two components. One is the current flowing through the branch impedance, another is the source current. So B trans I loop will be written as IB minus IS. Okay, for kth branch, this is IK. For first branch I1. So I want to say IN for all the branches will constitute IB. IS1 to ISN for all the branches will constitute IS. So B transpose I loop means IB minus IS. Alright. Similarly, this equation also we have derived. C transpose IB minus IS equal to 0 means C times IE equal to 0. Okay, this is representing the Kirchhoff's current law. C times IE equal to 0. IE again written as IB minus IS as before here, IB minus IS. Okay. Similarly, C transpose VT is written as VE, element voltage, or we can write C transpose VT equal to VB minus VS, because element voltage means voltage in the branch impedance, voltage drop in the branch impedance minus source voltage in the branch. Okay, so these are the equations, modified equations written from those original equations. Okay, where we have written AI equal to 0 or BV equal to 0 or CI equal to 0. From there, we have divided the element current into two components, one due to the current flowing through the impedance, another due to the current flowing current due to the source. Similarly, A transpose Vn equal to Ve, B transpose I loop equal to IE, C transpose Vt equal to Ve. These are written in the full form. A transpose Vn is Vb minus Vs, B transpose I loop is Ib minus Is, C transpose Vt is Vb minus Vs. Okay, these are the expressions we can write. So already we have developed the expressions. Now we are rewriting these expressions using the notation of the generalized branch. Okay, so that we may include any type of branches. Okay, whether voltage source, current source, impedance, anything. Now, what is branch voltage? Branch voltage drop. Okay,
স্যার
that bolo.
স্যার একজন ওরা ঢুকতে পারছে না, একটু দেখবেন।
Okay. So what is branch voltage drop? Branch voltage drop, we have written VB equal to ZB IB, branch impedance into branch current. Okay. Or IB, we can write as, what is IB? ZB inverse VB, and this is impedance. And what is this impedance? Is the branch voltage, branch impedance matrix. This is the voltage vector, current vector, impedance matrix. So branch voltage vector, branch current vector, branch impedance matrix. So branch current vector is inverse of the branch impedance matrix into branch voltage vector. What is the inverse of the impedance matrix? Obviously, this will be the admittance matrix. So this is the branch admittance matrix. Taking the inverse of the branch impedance matrix, we are obtaining the branch admittance matrix into VB. Okay. All right. Now you see what is the composition of branch voltage impedance matrix or composition of branch admittance matrix. So branch impedance matrix means it is basically branch to branch impedance. Okay. Obviously, it will have self impedance of the branch as well as mutual impedance of the branch. Previously, we have written ZKK, means we have written for expression for the branch impedance. Okay, self impedance of the branch. But if we allow, or if we consider the mutual impedances as well, or mutual coupling between the elements also being considered, then ZB will become like this. It will be Z11, Z12, Z13, Z14, Z1N. Similarly, Z11, Zn1, Zn2, Zn3, ultimately Zn. That means there will be self-impedance as well as mutual impedance. Self-impedance of a branch Z11, self-impedance of branch N, Zn. Mutual impedance between a branch and the other branch, it will be say Z1N, between branch 1 and branch N. Between branch 1 and K, it will be Z1K. Between branch 2 and I, it will be Z2I, like that. Okay, so there are self impedances at the diagonals and mutual impedances which are the off diagonal terms. Self impedances of the branches are diagonal terms of this branch to branch impedance matrix, and mutual impedances are written as the off diagonal terms here. The elements, those are not the diagonal terms. Okay. Now here you see that if ZB is the branch to branch impedance matrix, what will be YB? It is the branch to branch admittance matrix. It will be the inverse of matrix ZB is the admittance matrix, branch to branch admittance. Okay. Now you see that this branch to branch impedance matrix will have self as well as mutual terms. So when you write this expression, always you have to write VB equal to ZB into IB because ZB is a matrix. You cannot write VB equal to IB into ZB. But if you write the voltage of a particular element, assuming that there is no mutual coupling, then you obviously, as we have written here, how we have written here the voltage, it is ZKK IK or IKK ZK, same thing, because that is single element. But when you are rewriting in the form of matrix and vector, then proper notation you have to follow. Don't forget to maintain the proper sequence, otherwise it will be wrong. Okay, so VB has to be written as ZB into IB. IB has to be written as YB into VB. Okay, not VB into YB, not IB into ZB. All right, because this is the structure of the branch to branch impedance matrix. Branch to branch admittance matrix also will have the same structure, but here in place of impedance it will be the admittance structure remaining same. All right, now ZII, ZKK, etc., the self impedance of branch I or branch K. ZIM, this is the mutual impedance between branches I and M, and obviously if the elements are perceived, then ZIM will be equal to ZMI. Okay, ZIM and ZMI, they are equal. Now with this, now we can, what we can write, we can now try to derive the equilibrium equation of the network. That means the complete network equation now we shall write using the voltage source, current source, and elements of the network branches. Okay, for that, let us first write down the equation using matrix A. That means nodal incidence matrix or node to element incidence matrix. What is the KCL? We start from there. It is A times IB minus IS equal to 0. This is not the Kirchhoff's current law. A times IB minus IS equal to 0. Let us write this as AIB equal to AIS. So we can write A times IB equal to A times IS. Or A, what is IB? IB means YB into VB. IB we can write as YB into VB. This is IB equal to YB into VB. This you can write here, IB equal to YB into VB. That is equal to AIS. Okay, so same expression, IB replaced by YB VB, and it is AIS. Now, we also know that A transpose V not equal to VE means VB minus VS. This using a matrix, this you can write previous day on the previous class or day before previous one, we have written this thing. Now you can write VB, expression for VB equal to A transpose Vn plus Vs. From here, VB will be equal to A transpose V naught plus Vs. Okay. Now let us write the values. What is AYB? AYB VB. What is VB? VB means A transpose Vn plus Vs. Write it here. A transpose Vn plus Vs will be equal to AIS. So from here, I can write the equation here again by utilizing expression for Vb. So AYB A transpose Bn plus Bs equal to AIS. Okay, combining these two. So what I can write here, AYB A transpose Bn, AYB A transpose Bn, that will be equal to AIS minus AYB, okay, Bs, AYB Bs. So taking means you see that here it is AIS and AYB Bs. So let us take A as the common factor, then Is minus Yb Bs we can write. So Ayb A transpose Bn equal to A Is minus Yb Bs. Okay, or Ayb A transpose, that may be written as say Oin. I am writing Oin here. Why this is Yn? That we shall have to see. We shall have to verify whether it is Yn. What is Yn? Yn means the nodal admittance matrix. We can show later on that A multiplied by Yb, that multiplied by A transpose, it basically is the nodal admittance matrix of the network. Okay, so this multiplied by Bn equal to AIS minus YBPS. Okay, so this gives you the complete equation, equilibrium equation of the network using a matrix. So this is the nodal equilibrium equation. Okay, using the matrix A. Is it clear here? Would you understand the derivation? Or any problem, any difficulty? Tell me. Bolo.
স্যার ওয়াইনটা কি হবে বলবেন? স্যার ওয়াইনটা
Why?
ওয়াইএন
Yn. We have already considered the nodal analysis. Okay. In nodal analysis, how we have written the equation? We have written the I equal to Y into V. Okay. That means node currents equal to nodal admittance matrix into node voltages. That we have written and we have utilized that matrix also. That YA, that was the nodal admittance matrix. Here Yn represents that matrix. Okay, how this becomes Yn, that we shall have to see, but I am writing this as Yn for the time being, AYB A transpose. To verify that AYB A transpose is the node to element incidence matrix. This is the transpose of that matrix, and YB is the branch to branch admittance matrix. It can be shown that if you multiply this whole thing, AYB A transpose, then we shall get a matrix, then that can be identified to be Yn. That matrix you can identify to be nodal admittance matrix. How it can, you have to do it yourself, or I shall have to show. So you see whether you can understand this or not, or what you can do, you can take an example for the network we have written. You consider that a matrix, you consider that YB, you assume that for each element here in the network we have considered, each element has some admittance you consider, only the self admittance you consider for the time being, and then multiply that by transpose of matrix A. See what you are obtaining and match that matrix with the nodal admittance matrix of the network. Then you will be understanding why I have written, or why we can write Yn nodal admittance matrix in place of AYB A transpose. Okay, so you try that. If you can understand, it is very good. Otherwise, I shall have to show that multiplication as well. I shall show you. Okay, but first of all, you try to understand. You try to multiply this. You try to verify this, that AYB A transpose basically is nothing but Yn nodal admittance matrix. Okay, is it clear? How it is
Sir,
nodal
Yes, sir.
matrix?
Sir, here, sir, IB is equals to IK or IK minus ISK?
Which one?
IB is equals to IK or IK minus ISK?
IB means, you see, element current is IB minus IS, and IB where you have written is this is the current through the branch impedance. Okay, and to indicate the to actually identify this current for all the elements, we have written IB. So IB basically means vector of currents to the network impedance. Okay, and IB minus ISK means it is the element current through this element. Okay, and IK basically is the current through the impedance of the element. All right, is it clear?
Yes, sir.
Current through the impedance, that vector of current through the impedance of the impedance of the element. Okay, বলো আর কিছু আর কেউ? Any other question, any other doubt?
স্যার স্যার বলছি ওয়াই এনটা আরেকবার বলবেন, মানে মানে একটা এক্সাম্পল না বললে
হ্যাঁ, একটা এক্সাম্পল দিয়ে সুবিধা হতো। এক্সাম্পলটা এখন তো এখানে করা নেই, and also I cannot write now.
স্যার মানে প্রিভিয়াসে যে একটা যে গ্রাফটা নিয়ে মেন করছিলাম ওটাতে যদি বলেন তাহলে।
হ্যাঁ, আচ্ছা ঠিক আছে। এখানে ধরো this is a matrix A Y B A transpose. Okay, A Y B A transpose. So this is A. This is A. What is Y B? This is a full matrix. We can work with reduced matrix. Okay, we shall be working with reduced matrix. So excluding fourth row, this is matrix A. So once you know A, you can form A transpose also. Now what is admittance matrix? Branch to branch admittance matrix. You come here. So you have to consider the element 1 impedance is this reactance, the inductive reactance. Element 2 this resistance. Element 3 this resistance of the current source. Element 4 this total impedance. Element 5 this impedance. Element 6 this total. And element 7 is. So these are the things. So to make the things simple, let us write branch to branch admittance matrix as, say, Y11 for element 1, whatever may be the value. Let me write Y11 simply. Small y11 representing the admittance, self-admittance of branch. For element 2, it is basically a resistance. One upon that resistance will be the conductance, or in general term, this is the admittance. So, say this is y22. This one is, say, y33. This is y44. This together, I am writing y44 to represent this one, y55 to represent these things, y66 to represent this resistance as well as the series capacitor. Then it is y66 and y77 means basically this inductor. Okay, you represent that by y66. Okay, now you multiply. This is y11, y22, y33, y44, y55, y66, y77 will be a diagonal. So now you write AYB transpose. This is what is A. So you try to multiply this. A matrix, yeah, this matrix, this up to third row. This is A, write the YB and write the transpose of that matrix, the matrix, and now you multiply. Okay, you multiply this matrix by a transpose. Then the results you multiply with this one. You will get finally a matrix. You get a matrix. Okay, what is the dimension of this matrix? It will be, you will see that in this graph we have drawn, there are 4 nodes. We are excluding 1 node. So in that case, if we exclude 1 node, you will be obtaining 3 by 3 matrix. Okay, so here therefore you will see that if we consider 4, that will be 4 by 4. So now you multiply this matrix and the branch to branch admittance matrix, which is a diagonal matrix I mentioned earlier, and the transpose of this matrix. You see that you are getting a matrix which is having only the admittances at the different position. there will be self in the self element of the matrix. You will have the admittances also in the mutual element. That means diagonal terms will be admittances, mutual elements also will be admittances, and you will be able to identify that matrix as the nodal admittance matrix of the network. How? You will see that in the final product, the admittance matrix that you will be obtaining will have this value. At node 1, you will have y11 plus y12 plus y11 plus y22 plus y44. At node 2, we will have y22 plus y33 plus y55. At node 3, you will have self-admittance. You will have y44 plus y22 plus y66 plus y7. And mutual admittance, you will get minus y12 between in the first row, second column. In the first row, third column, you will have minus y44. Okay. Then in the second row, third column, you will have minus y55. In this way, you will see that in the first row, third column, third row, second column, second row, first column, this will be the mutual terms. Okay. So you will be in a position to identify the equivalence between the nodal admittance matrix for this network and the product A, Y, B, A transpose obtained from A matrix and branch to branch admittance matrix for this. Okay, you will be in a position to identify that. If any confusion, I shall show these things in the next. But I shall have to then write, multiply, and then show you. Okay.
স্যার
বলো।
স্যার বলছি একবার ওয়াই ব্রাঞ্চ যেটা ওয়াই বি ওই ম্যাট্রিক্সটার মানে ইন্ডিভিজুয়াল এলিমেন্ট গুলো হচ্ছে
YB means branch to branch. Branch মানে YB এর মধ্যে কি থাকবে? In the rows there will be branches. How many branches? 7 branches. In the column also there will be 7 branches. So YB will be a 7 by 7 matrix. Okay.
হ্যাঁ
So
তো স্যার এবার
বলো।
স্যার এ ম্যাট্রিক্সটা তো হচ্ছে 3x7 আর এ ট্রান্সপোর্টটা হচ্ছে 7x3, তো এটাকে আলটিমেট মাল্টিপ্লাই করলে 3x3 ম্যাট্রিক্স আসবে একটা।
আসবে আলটিমেটলি যে আসবে না, আলটিমেটলি যেটা ফাইনাল ফর্ম উইল বি বিটুইন নোডস এন্ড নোডস। ওকে,
আচ্ছা
নোডাল অ্যাডমিটেন্স ম্যাট্রিক্স এর যেরকম স্ট্রাকচার হয়, যেরকম ফর্ম হয়, দ্যাট ইউ উইল গেট। ইউ ট্রাই ইট ওয়ান্স। ওকে, you try multiply, and then since it is not done here, I have to do all this calculation. So doing this and then showing you, there will be so much of idle time. Better I should show you in the next class if you are in a trouble. Okay, so similarly for other matrices also I should show. Let me discuss it today, and example I shall take in the next class. There I shall show all this multiplication and finally what you are getting. Okay, in the meantime you try yourself. Okay, and in the final next classes I shall show all these things in more details, because these are not done here right now. Okay, now next let us go to write the network equation, equilibrium equation rather, using the B matrix. B matrix already we have formed. Okay, we have also written Kirchhoff's voltage law using B matrix, also defined relation using generalized network parameter network branch we have shown. So now you start from here. Now you start from here, that I have shown. Now you start from this B matrix. For B matrix we can write KVL, Kirchhoff's voltage law, as BVE equal to 0. So V again is VB minus VS. Okay, branch voltage drop VB minus VS. So VB equal to VS we can write from here. V times VB equal to V times VS. This is what we can write. Now VB, how can you write? It is ZB into IB. Branch impedance matrix or branch to branch impedance matrix into branch current. Branch current means current through the impedance of the branch. Okay, so B times ZB ID, the IB, that becomes equal to B times VS. Now B matrix, you see, this is nothing but the loop 2 element incidence matrix. Okay, so basically by using B matrix we shall be solving loop equations that we know, and therefore we have written B transpose I loop as equal to IE. So that IE also we have shown to be equal to IB minus IS. Element current has two components. One is the current through the impedance of the element, and other is the current source in the element. So that is written as IS. So element current is IB minus IS. Okay. Now B transpose I loop equal to IB minus IS. Here, what you can do, you can replace this IB by taking IB from here. IB may be written as B transpose I loop plus IS. Put it here. BZB, IB means B transpose I loop plus IS. Okay. So from here, put the value of IB here and BVS you are writing here. So BZB, B transpose I loop, this product is equal to BVS minus ZB IS. So BVS here minus ZB into IS. Okay. This is what we have obtained. Now what we do, again we are writing this. BZB B transpose. Say let us write this as Z loop. Okay. So if you multiply again B matrix by Z, B means branch to branch impedance matrix, and then multiply this by transpose of the B matrix, you'll see that ultimately what you are getting, that is nothing but the loop impedance matrix for that network. Okay, so BZB B transpose is the loop impedance matrix. I am writing it here, Z loop, without verifying that this is Z loop. So we shall have to see that, or we shall have to establish that this basically is representing Z loop. How to establish that? Again, you consider that basic network we have considered. You write the expression for, you write the matrix for ZB, then you find out this product. Also for the loops identified for this graph, okay, you write from the loop impedance matrix. You see that they are representing the same matrix. So BZB B transpose may be written as the Z loop for that particular network. Okay, so again you try to verify this. In the next class, again I shall do this. I shall show that this is possible, or this is actually representing the same thing. So this into Z loop will be equal to BVS minus ZBIS. So therefore, this represents the network equation where we have included voltage source, we have included current source, we have included the impedance of the network. Everything has been included. So in terms of B matrix, loop to element incidence matrix, we have written the network equation, or this is the equilibrium equation of the network in loop frame of reference. Okay, using loop analysis technique, this is the equation that has to be solved. All right. So now again here, you have to check that this product BZB B transpose is basically representing this loop impedance matrix. If you try using the steps I have already mentioned, the writing B is already written. So you write the ZB matrix, you multiply, get the result, and also you, for the identified loops, what is the identified loops for this graph? You see that identified loops are, these are the loops. There are 4 loops for this loop, for this 1, 2, 3, 4 loops. You form the loop impedance matrix. Okay, what will be the loop impedance matrix? Sum of impedances in the loop would be the self impedance. What will be the mutual impedances? If we write all the currents to be in the clockwise direction, or all the currents in the same direction, then in the common impedance between two loops, direction of loop currents are opposite. In that case, the mutual impedance comes as a negative impedance, minus negative of the common impedance. But if why that was coming in that word, because we have assumed the loop currents, all loop currents to be in the clockwise direction. We have assumed that's why what happened in the common impedance of the loops, currents are in the opposing direction. Now, loops are not identified in that way. How we have identified the loops? By seeing the direction of the element that becomes the link forming the loop. Okay, therefore, now you see that in this common impedance between loop 1 and loop 3 and also between loop 4, what have happened is that this impedance, it is common and it is sign loop current here, here, they are all in the same direction. So now obviously there will not be a negative sign. Okay, it will no longer be negative, rather it will be a positive impedance. Okay, so you would understand this and try to verify this, because previously if you write the loop current in this direction and this loop current in this direction, then through this impedance current are in the opposite direction. That's why the common impedance of two loops, or which is the mutual impedance between two loops, appeared as a negative impedance. Now what happens, because of this type of loop current selection along with the direction of the loop current, you say that now through a common impedance, this current, all the loop currents are in the same direction. Since all the loop currents are in the same direction, obviously now the impedance, mutual impedance, will not be a negative impedance in for these loops. Similarly, between these two loops, you see, between loop 1 and loop 2, this is the direction of loop current and this is the direction of loop current. Again, through this branch, both loop current and loop current 2 are in the same direction, so they will not be negative. Between, say, loop 2 and loop 3, what happens? Between loop 2 and loop 3 currents in this direction, loop 2 currents in the opposite direction. So here they are in the opposite direction, so it will be negative. That means when the loop currents are in the opposite direction through a branch which is common to two impedances, two loops, then the mutual impedance will be a negative impedance. But if all the currents are in the same direction, okay, that means the common, through the common branch of two loops, if the currents are in the same direction, then loop impedance also, mutual impedances between loops also will be positive. Okay, if the currents are in the same direction, it will be positive impedance. Currents are in the opposite direction, it will be negative impedance. So in this way, you write the loop impedance matrix, then also obtain the product B, Z, B transpose and match these two. See whether they are representing the same thing or not. Okay, is it clear? বুঝতে পেরেছো?
Yes, sir.
Okay, but you try to verify this, and I shall again do it in the next class by taking one example. Then this will be established rather. Okay, this will be established there. I shall show it.
এখানে স্যার আমরা যখন যে ব্রাঞ্চ ইম্পিডেন্স বা ওই ব্রাঞ্চ হচ্ছে অ্যাডমিটেন্স ওই ম্যাট্রিক্সটা যখন করব, তখন মানে ওগুলোর মধ্যে যে ওই প্লাস মাইনাস সাইনটা যে কিভাবে নেব, মানে যে মিউচুয়াল যখন থাকবে তখন যে অপোজ করলে মাইনাস
ইম্পিডেন্স লিখছো, যখন ব্রাঞ্চ ইম্পিডেন্স গুলো লিখছো, if they are self impedances, for the time being you consider self impedance only. Don't go for mutual impedances. It will be rather more complicated. Then I should show it how to consider mutual impedances. Okay, তুমি প্রত্যেকটা ব্রাঞ্চের শুধু সেলফ ইম্পিডেন্স আছে এটা ধরে নাও, তাহলে তো আর কোনো সাইনের ব্যাপার নেই, all will be positive. Mutual impedance, that appears the question whether to consider that impedance as positive or negative. So that I shall deal with some example in the next class. Okay, therefore branch impedance, that means branch to branch impedance, if they are only self, then all impedances will be positive impedances. Okay, there is no question of any negative impedance. An impedance will be negative or positive depending upon whether that is direction of current with respect to the dot. Okay, that will be regarding the mutual impedance. So that mutual impedance, let us for the time being avoid that, because that will create confusion. First of all, try to understand it with the help of self impedances only. Okay, once that is done, then we shall go for the mutual impedance. Okay, otherwise for writing the self impedance matrix, or self-admittance matrix, all elements will be diagonal elements and all impedances or admittances will be positive. All right, but when you form the
Mutual
nodal
impedance
admittance matrix or loop impedance matrix, then you see where what the direction comes and try to explain that. Okay, that explanation and establishing the direction and everything that will be done on the next class. I should do it. I should show it. Okay.
Okay, sir. Okay, sir.
Now, but you try to understand on your own first. Okay, I should show you. Obviously, I should show you with example, but you take the example given here, try to establish that on your own, then I should do. Okay.
Okay.
Now, let us write the equation using the C matrix. Okay, again, the equation will be nodal equilibrium equation. Nodal equation, but nodal equation, the variables here will be somewhat different. Already I have mentioned these variables and the variables you consider while you write the equation using A matrix, they are different because when we write the A matrix, then the conventional nodal analysis where node variables are taken as variable. But when we consider the cut set matrix C, then equations are nodal equations, but the variables are not the node voltages. Variables are the node pair voltages. Okay, node pair voltage. What is the meaning of node pair voltage? Node pair voltage means voltage between two nodes is considered as variable. Obviously, node voltage is also our node pair voltage because in the nodal voltage, conventional node voltage, where reference node is common. So there also it is a node pair voltage, but that is a node and the reference node. Those two nodes are considered as node pair. Since the reference node is the common node, generally we don't say that node, we don't tell that node to be that two nodes to be node pair. That we call the node voltage, expressed with respect to a common node. In case of writing equations with C matrix, there that reference node is not fixed. Rather, there is no reference node at all. What we should do? Rather, we shall be using the voltage between two nodes as the variable. And this between two nodes, basically, it will then represent a network element. Which element? Basically, the element of the network tree. The element of the tree are considered as variable. That means tree branch voltages are considered as variable. Since tree branch voltages means voltage between two nodes across the branch of the tree. Two nodes are across the branches of the tree. So that's why these variables are called node pair voltages. Rather, instead of node voltages, we say they are the node pair voltages. Am I clear? Okay. So now here you see that I can write Kirchhoff's current law as C times IB minus I is equal to 0. C times IB minus I is equal to 0. Okay. Again, as before, this derivation is very simple. CIB is CIS. I can write it. It is the branch current vector. It is the source current vector. Okay. IB may be written as YB into VB. So CYB VB equal to CIS. Also, from this relation, that C transpose VT equal to VE element voltage. So there is a bracket here, obviously. Okay, C transpose VT equal to VB minus VS, or C transpose VT equal to VE. What we can write? We can put it here and write CYB then VB. This VB you put it here. C transpose VT plus VS. C transpose VT plus VS equal to CIS. So rearrange this. CYBC transpose into VT equal to C IS minus YBVS. So C IS minus YBVS here. Now it is CYBC transpose into VT. CYBC transpose C means obviously a matrix of 1, minus 1 and 0. C transpose also is that of nature 1, minus 1 and 0. So obviously this product will have only admittances, and that admittances may be identified to be the say nodal admittance. Okay, where this nodal admittance matrix is somewhat different from the nodal admittance matrix we have formed using A matrix. That means both are admittance matrix, but the admittance matrix that we have formed previously using the A matrix is a conventional nodal admittance matrix where a particular node is taken as reference. In this case, that particular node is not the common, so therefore we can say that this admittance matrix basically is related to card set, or you can say this is the card set admittance matrix that I should show you. This basically is the card set admittance matrix into tree branch voltage is equal to C times IS minus YVPS. Okay. So by multiplying the CYB C transpose, you will get a matrix that you try to identify the relation between this matrix Yn and the cut set of the graph. Okay. So you find out this matrix, this product, and see how you can relate the product with the cut set of the network. Okay. So for this particular example, you try to establish that. I should show you, obviously in the next class I should show you how they are related, but first of all you try on your own to establish this relation, to identify that relation, or try to explain how this admittance matrix is related with the cut set, with the element of the cut set. Okay, they are polar sign and their value, everything, how they are related. Okay, so once you can do this, you can write this. Obviously now this is completely written, that equilibrium equation you have formed using the cut set matrix. That means basic cut set to element incidence matrix. Okay, so using this A, B, and C matrix, therefore we can write network equations. Okay, and after writing network equations, you are now in a position to solve for Vt. If you solve this equation, obviously you will be obtaining Vt. You see that you can very easily write this, solve this equation, because Yn cut set matrix, you know the branch to branch admittance matrix, so Yn will be known. Then you can calculate Vt by taking the inverse of Yn and multiplying with this. Here C is known, Is is the source current vector, this is also known, Yb branch to branch admittance matrix is known, Vs is also known. So when you solve this matrix, solve this equation, you will be obtaining the tree branch voltages. Means you will be obtaining the voltage across the elements of the tree branch network tree. Okay, so this is how this cut set matrix is helping you in solving network using the tree branch voltages as variable. This we have not done previously. Using cut set matrix, we are doing this. Similarly, once you write this matrix, okay, so once you form the Z loop, then obviously you can solve for I loop. B is known, Vs is known, ZB known, Is known, Z loop also you can form. You can obtain this multiplication, so Z loop will be automatically obtained. So take the inverse of this loop, pre-multiply this one by inverse of Z loop, then you will be obtaining the loop currents. Once you obtain the loop currents, then you can find out the element current. Okay, very easily. In the same way also, you can write this expression. Then you can form this matrix, this product, nodal admittance matrix will be obtained. Then obtain the node voltages as the inverse of this matrix and multiply that by this one, you will get the node voltages. Once the node voltages are obtained, from that you can find the element voltages. So everything regarding the solution of the network can be done using the graph theory, using the matrices used for the representation of the network, representation of the graph, representation of the loop and cut set for the network branches and network graph. Okay, so that is how we can write the equation and solve it. And then now we are in a position to apply that for solving network equations. So I shall not explain this equation today because it will involve mutual impedances. So before that, we shall be dealing with the self impedances and self admittances, and then we shall verify this. We shall solve some network, and then only I shall go to, or I shall move forward to right to solve this one. So this is a very simple, but I think it is better to skip this today, and rather better we solve some simpler network where there is no mutual coupling. Mutual coupling will be considered afterwards. First of all, let us solve network having no mutual coupling. Okay, that will be easier. So what we'll be doing, we'll be considering the example that was used for explaining the graph theoretic definitions. We have written the expression for, we have developed A, B, and C matrices, and you write, assume that all the network elements are having self impedances or and self admittances only. Z11, Y11, these are the self impedances and admittances. Now use those admittances or impedances as the branch impedance matrix, then multiply using the network matrices, okay, incidence matrices, and try to establish the relations. Okay, try to identify that BZ would be transpose is representing the loop impedance matrix, AOIB transpose is representing the nodal admittance matrix, and COIBC transpose is representing the admittance matrix. You try to relate that admittance matrix with the cast set of the network. Okay, with the cast set of the network graph. Once this is done, we shall proceed for other examples. So that I shall do in the next class. Now, if you have any questions, you can put those questions to me. বলো, আরো কোনো প্রশ্ন আছে? Any questions? Do you have anybody? Balo, any questions? So if you don't have any questions, then we shall stop today. Because I am going for roll call, and then today is Friday. Again, we shall meet on Tuesday. Okay, Tuesday. Therefore, I shall deal with some examples on graph theory applications. Okay. Well, anybody having any questions? No. আচ্ছা, তোমরা বলো তো, তোমাদের অনেকে আসছো না, তোমাদের এমন কি কেউ আছে যে কোনোদিনই আসেনি? Anybody? Particularly that girl, perhaps her name is Anita. Okay. ও কি তোমাদের সেকশনে না অন্য সেকশনে আছে অনিতা?
স্যার আমাদের সেকশনে।
তো ও তো কোনো ক্লাস করেনি বোধহয়।
স্যার হ্যাঁ, মানে ওর কাছে প্রবাবলি মোবাইলটাও পৌঁছে গেছিল, মানে তা তো জানি না ঠিক, মানে করছে না।
মোবাইল পেয়েছিল?
হ্যাঁ, মনে হয় মোবাইল টোবাইল পেয়ে গেছিল।
আচ্ছা, তাহলে ওর সঙ্গে যোগাযোগ করো তোমরা। ওকে কি তোমরা এগুলো পাঠাচ্ছ? ও তো মেইলে,
স্যার ওর সঙ্গে যোগাযোগ করা যায় না, মানে ফোন টোন করলেও ধরে না। মানে আমরা চেষ্টা করি মাঝে মাঝে ফোন টোন করে আপডেট নেওয়ার, কিন্তু মানে ওই একটু ফোন টোনও ধরে না বা কিছু এরকম করা অসুবিধা হয়ে যায় যোগাযোগ করা।
অসুবিধা হচ্ছে, কিন্তু গ্রুপ মেইলে তো আছে।
স্যার গ্রুপ মেলে আমরা মানে ওর কাছে চলে যাওয়ার কথা, মানে অ্যাকচুয়ালি আমরা গ্রুপ মেলটা অফিসিয়াল গ্রুপের মধ্যে দিয়ে করি। আমাদের একটা হোয়াটসঅ্যাপে অফিসিয়াল গ্রুপ আছে, আমরা ওটার মধ্যে আমাদের সব যাবতীয় লিঙ্ক টিঙ্ক দিয়ে দিই। মানে আপনি ওই গ্রুপটাও আছে, মানে আপনার ক্লাসটা হয় যে
সেটা জানি। এবং এই যে আমি যেগুলো তোমাদের ফরওয়ার্ড করলাম লেকচার রেকর্ডিং, সেটা কি ওকে ফরওয়ার্ড করেছো তোমরা? মানে ও পেয়েছে কি?
হ্যাঁ স্যার, মানে আমরা ওই লেকচারের রেকর্ডিং গুলোর লিঙ্ক গুলো হোয়াটসঅ্যাপ গ্রুপে